we have a carbon atom. And Mr. Carbon, show them your electrons. How many
Now
of them?
here we've got 4 electrons.
1, 2, 3, 4.
Okay. Carbon in group 4. So they are the valence electrons.
Group 1, hydrogen. Each hydrogen has 1 electron. So very little difference. This doesn't hold its electron any more strongly or weakly than that one, roughly speaking. And so what's going to happen now is that each one of these would like to pair up with another electron. Hydrogen, single electron, would like to pair up with another electron, and it's going to do that. There.
Oh, there we have
Well, I don't think
one.
we've got quite enough hands here, but we'll...
Well,
Okay, those 2 electrons now are going to share. Are you going to do a little balancing
let's
act
try
here?
and do that.
Okay.
There we
And
go.
this one will pair up there, and that one will pair up there. And you can see now there are 1, 2, 3, 4. Okay, there they are. 1, 2, 3, 4. Now this is why we do Lewis diagrams, and we don't try and balance ping pong balls and so on. So let's just have a look at this one. You see, when we get 1 electron from a hydrogen, we're going to get a pair. You get another electron from another hydrogen, you're going to get a pair. You get a third, and you get a fourth. And you see what we have is a lovely, pretty picture of 1, 2, 3, 4 bonds. That is the molecule CH4, and we will see in a little while what kind of shape it has. But for the moment, we are happy with the fact that we've got a carbon and 4 hydrogens. That means 4 carbon-hydrogen bonds. And let's just have a look at another feature of those bonds. Here they are. You see the bond length is about 109 picometers. That means 109 times 10 to the minus 12 meters. That's the length of each of those bonds. And we see that we have a bond energy of about 413 kilojoules per mole. That means to break all 4 of those bonds on average would cost us 413 kilojoules for every mole, and I'm sure we all know what a mole is. That if you don't understand the mole concept, go and have a look at it in the textbook. But for 1 mole of carbon-hydrogen bonds will cost you that amount of kilojoules of energy to break them.
Now we have been able to have a look at what we call single bonds. Everything we have discussed so far are single bonds. What happens when we have more than 1 bond forming between atoms? And that is what we call multiple bonds forming. What happens?
Okay.
That's what we're going to look at now.
Probably best to look at our Lewis diagrams again.
Yeah.
Let's take the example of carbon again. And carbon, as we know, has 1, 2, 3, 4 valence electrons. An oxygen here would have 1, 2, and you see how I'm drawing this now. 1, 2, 3, 4, 5, 6. These are single electrons which are looking for a share of another electron. Now we've got 2 bonds being formed between a carbon and an oxygen, but the carbon is still not fully replete or satisfied. It hasn't got enough electrons yet. It would like to share these electrons. So why don't we find these are dots, I forgot. Another oxygen to satisfy those others. What we get here is a carbon and what is called a double bond. A double bonded carbon oxygen bond. Now if we have a look at our bond strengths here, you see that the bond strength between carbon and oxygen was 358 kilojoules per mole. Now it doesn't really matter if we don't understand exactly what this unit means or what the size of that unit is, but relatively speaking, look what happens when we get a double bonded carbon oxygen.
Sure, the bond energy rises to something like double of what we had first.
And that's more or less what we would expect, wouldn't it? Okay, but you see the interesting thing is it doubles in strength, double bond, it takes twice as much energy to break it, and that's kind of what we would expect. That's what we find in carbon dioxide. That also tells us that carbon dioxide is a pretty stable molecule. Okay,
Yeah.
it's not going to break its bonds very easily.
You
or have
need a
them
lot
broken.
of energy to break it.
Okay, and we can get double bonds in any molecules where there are two to share. Let's just have a look very quickly then at oxygen and see how oxygen, and I know that this picture is getting fairly full, but there we had our ionic bond. We've looked at what happens with the bonding in methane. We've seen CO2. And now let's have a look at oxygen. It's got, again, 1, 2, 3, 4, 5, 6. And another oxygen, 1, 2, 3, 4. Those are pairs of electrons.
Yeah. 5, 6.
And so you see what can happen with oxygen is we can form what is called a diatomic molecule. Diatomic means two atoms. A diatomic molecule of oxygen. Now, I've got to find space on this piece of paper somewhere to show a wonderful case of nitrogen. 1, 2, 3, 4, 5 electrons. One less than oxygen. It's one to the left of oxygen on the periodic table. Now, we get another nitrogen coming along here. 1, 2, 3, 4, 5. And yes, trust yourself, it does happen. Nitrogen, 1, 2,
Triple
3.
bond.
Triple bond. So nitrogen molecules, the diatomic of molecule of nitrogen is a triple bond. Now let's talk about this for a moment. Nitrogen forms 78% of the air. When we breathe in, 78% of what we breathe in is nitrogen. It doesn't react with the blood in the way that oxygen does. Why doesn't it react?
Because to break up the triple bond, you need a lot of energy. That's why it is not as reactive as oxygen.
And you know what? For a long time, nitrogen was regarded as an inert gas, almost inert, just like all of these other inert gases that don't react, because those three bonds
are very strong.
Very strong.
Very strong.
Now, we've spoken about bond energies. We've got to start talking about molecular shape now.
Now, during chemical reactions, what is discovered is that there is some way in which these molecules and atoms react and interact with each other. And it has been discovered as well that this reaction or the interaction is also influenced by the shapes in which these molecules are. And therefore, in our next lesson, we are going to look at these shapes and how they come about.
And the shape of molecules, as Taniko has just said, how they come about and what those shapes actually are very important when we look at how molecules interact with molecules. Sorry, that's repeating what you've said. Let's go and do it in more detail next time.
Thank you so much. Thank you for watching. We are signing off now. It's Tinyiko Wamachavkosa. Bye-bye.
And Peter Glover without such a fancy middle name.
Summary. In this lesson, you learned about multiple bonds, oxidation state and oxidation number, valence shell electron pair repulsion, molecular geometries, ionic liquids and electrons metals, electron band theory, conductors and insulators and semiconductors.